Hello. Today we're going to learn about torque and torsional shear stress. Now, torque, T, is a moment that causes a twisting deformation across a member. An example here is given for a cylindrical beam, where we're applying torque, a torsional moment about the x-axis. This twisting motion uh, creates shear stresses that develop across the cross section of the sample, but it also creates a angle of twist, a literal change in shape of our cylindrical beam when subjected to that moment. Now, the angle of twist, angle theta, is calculated as follows, where it's equal to the torque that's applied times the length of the member divided by G, which is the shear modulus of the material, times J, the polar moment of inertia, right? Now, the stress that is applied, the torsional shear stress, can be calculated as follows, where tau, torsional shear stress, is equal to the torque that's applied to the body times the distance from the neutral axis, so from the center of the beam to your point of interest, divided by the polar moment of inertia. And where torsional shear stress is maximized at the outer radius, at the outer edge of a geometry. Now, we've got an equation here for torsional shear stress. We can see that it's a linear equation, that as we move from the neutral axis to the outer edge, it becomes larger. And so we can then draw a diagram for how torsional shear stress is distributed across a member. We can see that at the center, if we're sitting right at the neutral axis, torsional shear stress is 0. And as we move to the outer edge, it moves to a maximum value. And this is true on any radial line that we would draw through our cross section or through a circular cross section that is maximized everywhere around the outer edge, that it is linearly distributed from maximum to 0 to maximum across the cross section, right? Now, in order to solve for the torsional shear stress, there is a parameter that we need to find, which is called the polar moment of inertia, J, where J is equal to the integral of the radius squared over a differential area. This could be rewritten as the integral of x squared plus y squared, because this is equal to the square root of x squared plus y squared, right? Over a differential area. Now, if we look at this expression closely, we can actually divide it out and find that the polar moment of inertia is equal to the second moment of inertia with respect to x plus the second moment of inertia with respect to y. So if we already have these two parameters, we can sum them together to get J. If we don't, if we have some complex geometry, we may need to solve the integral. So let's look at an example. An example here, we've got a circular cross section, all right? And it has a diameter of D. And we go to an appendix, and we find that the second moment of inertia with respect to x and y is equal to pi times that diameter to the power 4 divided by 64. Well, to get that polar moment of inertia, if we double this, or this plus itself again, then we find the polar moment of inertia, which is, the same thing, but divided by 32, right? Now, for many common simple geometries, the polar moment of inertia, as well as the second moment of inertias, can be found in Appendix A18 of our textbook. So it's very useful if we've got some simple shapes to go ahead and just go to the appendix and use these closed form expressions directly. But if we have some complex geometry, or say a composite body, we may have to do the integration. We may have to actually go and solve for these parameters, or we may need to use the parallel axes theorem in order to solve for these parameters. Now, thus far we've looked at circular cross sections and the torsional shear stress, but what about non-circular members? For non-circular members, we can't make the assumption that the shear stress is linearly distributed and it's maximum everywhere on all the edges. And for a rectangular cross section, the shear stress is zero at the corners where the distance is largest. And so we have to do something special when we're dealing with rectangular cross sections. Now here is just a graphical example of the angle of twist we would see in a rectangular type of cross section with dimensions b times c, right? So we have a very interesting twisted shape in the geometry. We have kind of a waviness to the edges. And when we look at the stress distribution, we can also see that the stress distribution is non-linear. So there's no linearity in its path, but also it's not symmetric. It's not symmetric around this rectangular shape. And so then how do we deal with it? Well, let's note that, we could write stress equations for the non-circular sections, but it's great in order to draw those expressions. It's pretty complicated. So instead, what we can do is we can use an approximation or a simplified form of those equations. Here's one of the expressions, the maximum torsional shear stress in a rectangular bar. So this is a simplification where tau max for a rectangular bar is equal to the torque divided by a parameter alpha times b times c squared, where b and c are the dimensions of our rectangle, was approximately also equal to the torque divided by b times c squared, with, in brackets, 3 plus 1.8 divided by b over c, right? So this is simplified equation. Let's look where for this equation to work, this is when b is a larger dimension than c, right? Now the angle of twist, another simplification, we can say the angle of twist theta is equal to the torque times the length of the member divided by beta, which is a parameter, times b times c cubed times g, which is the shear modulus of our material. Now the parameters alpha and the parameters beta, these parameters, can be obtained using a lookup table provided in our book. In section 312 of the book, we are given this lookup table, which tells us the approximate values for alpha and for beta for different ratios of the dimensions b over c. So if we know the ratio of b over c is, say, 4, then the alpha for our cross section is 0.282, and the beta for our cross section is 0.281, right? So this table and the simplified equations allow us to deal with non-circular cross sections in a simple way. And with that said, we've learned what we need to know about torsional shear stress.